Now let's talk about the maintenance approach maturity across organization and how it is applicable to ONGC. So this is a pictorial representation which shows the maturity of the maintenance practices over the period of time. So earlier it used to be a reactive maintenance, and with the period of time it evolved to planned, then preventive, then condition based monitoring, and finally it is about predictive maintenance. And the future to the predictive maintenance is the proactive maintenance, which can also be said a predictive plus prescriptive maintenance. Based on it, you can clearly see where we are standing. So ONGC is presently in the era of somewhere between condition based monitoring. Now the idea is to scale it to the predictive maintenance. What are all the benefits associated with the predictive maintenance will be covered in the upcoming slides. So you can see that the idea evolves over the period of time. So many of the seniors which have joined early in the ONGC have witnessed reactive maintenance, and over the period of time as the organization evolves, it has moved to preventive maintenance. Now let me discuss about the preventive maintenance solution description. Why there is a need for this predictive maintenance. So 3 points we would be talking about: pain points, why there is a need of it, and how we are going to address it, and what are all the value propositions that are being delivered. So predictive analytics needs to be done for the critical assets, and what earlier there used to be analysis done through this spectrum analyzer and through manual entry. There was no visibility of how historically the machine has behaved over a period of time, which has led to loss of benchmarking of data, and it also does not give us a prescriptive insight like how does various OEMs machines have progressed over the period of time. So how we are going to address this situation? So first key step is the data analysis. Like the data is to be studied not as a single point of view. It has to be viewed from a broader perspective, considering that the data is available in the electronic form, so that it can be comparable with the similar kinds of assets and of similar service conditions, based on which the model is being tuned. Now how is it being trained to the artificial intelligence and the machine learning? You have condition based monitoring maintenance calculations available with you. You integrate it with the AI ML and you have a huge data set that can be a game changer for us. So what are all the key benefits associated with the AI ML is that it can figure out what are all the missing elements. If there are so many historical data is available, that can also be very well predicted. It can also tell us like if any equipment is going to bad, or if there is some serious operator intervention which needs to be required. So what are all the values it has delivered? It helps us in increasing the mean times between failure and reduces the mean time to repair. It also enables to have the risk-based maintenance approach in plant operations, and there is also a significant improvement in the sense there are increases in the early warning detection, so that maintenance can be planned well ahead. Also there is a reduction in the maintenance cost. Now how we are going to achieve this? So depending upon the criticality of the asset, it can be decided that there are 5 major categories. Some are safety critical, reliability, some are production critical, redundant assets, and the cost of repairs. So based on which there can be 3 priorities, like the equipment which are highly safety critical, and you know which one is the bad actor, and also what are all the use cases of the failure, and there are adequate instrumentation available to measure the key parameters. On the second hand, priority 2 can be given to the high safety critical equipment, but there are known failure mode, but there is an adequate instrumentation also available. Priority 3 can be given to the medium safety critical equipment, for which the instruments are also available and failure mode are also available, but who is the major culprit, that is unknown, as an unknown factor. So this was the case study which is being done in one of the pump and heat exchanger unit in the major oil company. So initially the client did not have the asset management strategy, in which their solely focus was on the individual asset, and the life of the asset was quite unreliable. So how they were doing it, they were purely going through the preventive maintenance and the reactive process. Now once you digitalize this whole thing, there is a visualization platform and asset performance metrics which can tell you like which one is the bad actor and how many are the instruments or assets which are operating beyond the IOW limits, and what are all the assets which are under risk. And also with the help of this, there can be a proactive asset strategy, there can be a risk-based maintenance, and a data-driven decision making is also available, so that there is a balanced cost and asset risk also decreases. What are all the final objectives? Integrated asset maintenance strategy helps us in having the alerts at a very very primitive stage, and also can predict the failure which is going to happen quite early. It can help us to have the shutdown in a planned manner and can have increased production and spare time to repair, and also helps us in reducing the inspection cost. There is overall improvement in the mean time between failure of a pump and mean time between failure of a heat exchanger by 849 and 976 days, which indirectly helps the organization to achieve this. Now this is one predictive maintenance approach which has been used by one of the industry for compressors. How they are doing it? They are maintaining what are all the key parameters for the compressor, such as the vibrations of the shaft, bearing data, temperature, motor current, and operation and safety limits which is available from the operator manuals. And that whole data of the compressor is being fed into a machine learning model such as the Markov model. So what does this Markov model does is it will continuously evolve the state change of the data over the period of time. Like we are able to figure out like how does a compressor behaves in a period of time from one state to another. So that state 0 can be configured as the state at which can be a normal state. State 1 can be a minor fault. State 2 can be major fault. State 4 can be the breakdown of the equipment. So this model continuously tells us that how the state transition is taking place, and based on which we can estimate what is the next failure time. Another one is the vibration regression model approach, in which the trends plots of vibration data is being plotted. So what is being done is the average of the vibration value is being plotted, and it is being compared with the normal point is being compared with the filter data. So what we are going to predict is by the next failure time how the model is going to behave. So what it leads to this annual saving of 12 million euros, and also increases the replacement cycle by 200%, which is a very good factor. And it can also help us in the higher asset availability and reduction of the downtime. There is another case study based upon the predictive maintenance approach for the pumps. So this is basically a neural network model for the pump performance, in which the key parameters for the pump is flow rate, discharge pump pressure, motor power, suction pressure, temperature, and the vibration. These are the key performance for the pump. And how we are going to predict is, we have captured the sensor output versus the expected output. How the model is being able to predict that, it will tell you like ideally what should be the head of the machine, head of the pump, comparison with the model, which will tell you what should be the predicted head. And if it supersedes, then the machine is then the pump is behaving very nicely. And if there are certain deviations, then you can say that there is something wrong with the pump, and based on which an corrective action can be taken. Similarly, it can be a design output versus the expected output. How does the machine is behaving with the design capacity or data sheet, with it can be the key area which can tell us like how the pump is going to work. So the moment there is a shift in the predicted head as compared with the design head, there are higher chances of the failure of the machine, and it will lead to an alarm. So based on which we can figure out like how we can improve the pump functionality. How we can predict the predictive maintenance approach for a heat exchanger is also a very interesting thing. So what are all the key parameters for the heat exchangers are the efficiency and the rate of fouling and the log mean temperature difference. It can be it can tell us like how good the exchanger is working. So what are all the analytics that we are going to run is the heat exchanger efficiency and heat exchanger log mean time differential. So the rate of degradation can also be compared, and the outcome can be the fouling alert or the fan malfunction alert. So this is how a predictive maintenance approach can be applied for an heat exchanger. Now this is what the predictive maintenance solution that we have implemented at Uran plant. This was the architecture that we have published in our tender. In this there are two key things to notice, is that on the left hand side there is DCS, and on DCS, which is having the process data as well as the field data from the various sensors and field instruments, and that data from the DCS is going into the historian, and some of the machine data is also available in the system 1. That data from the system 1 is sitting in the level 1, or you can say the control layer, and layer 3 is having where the process historian or enterprise wide historian is sitting, that is CRTDMS. That CRTDMS is having the capability to interact with the predictive maintenance solution. That solution is having the that preventive maintenance solution is having the capability to have this data import capacity as a manual form, as a data from the analyzer, also lab data. It may be an oil analysis data or the performance curves from the machine, based on which it will tell us like how good the model can be developed, and on the background the various machine learning and artificial intelligence algorithms would be running, which will tell us like how the system is working. And on the top of it there is a visualization layer which can tell us like what are all the values which are available in the initial stages, and if there are any deviations from the process limit, and it can be further drilled down to the SAP system for generating the maintenance order. This is how a digital predictive solution works in general. So there are 5 key elements which are associated. The first key step is to identify the data points and the data sources. The data sources are from different categories, such as the machine data or the design data, for LIMS data, SAP data, and the real-time OT data. The acquisition of that data is a very important stage, which is the stage 2. Now this data is being processed and the model is being developed. In between there are 2-3 steps, that is the structuring of the data in a well defined format, so that the model understand and it can figure out if there are any missing values, or say if there are any outliers, or there are any anomalies in the data, based on which a suitable model of the asset is being created, which is nothing but your digital twin, up to some extent for a compressor, or for the whatever the equipment or asset which we are creating. That asset would be trained over the historical data, and based on which it will extrapolate the things, and it can predict the what are all the failure modes, and it can predict based upon the advanced neural networks algorithms. How is it going to work for the model validation and analytics is, as soon as is a failure, it will be reflected somewhere between it will be reflected somewhere between the curves which is being plotted, which will tell you like how the equipment is going to fail. And there is also error metrics for the performance of the algorithm to figure out like which one are the false positive, which one is the false negative. And on top of it is the visualization layer, which is the basically HMI for the end user or for the various stakeholders. It can tell us about the data from the historian, SAP and other sources, and also what are all the failure severity for the assets. Along with it, what are the anomalies that are being detected using the threshold monitoring, so that if the alarm goes beyond a particular limit, then a suitable action can be taken. It can also tell us about the real-time alerts for the critical parameters, and what are all the bad actors, and how historically they have performed over a period of time can also be predicted through them. So at Uran we have done it for 8 compressor, and based upon the availability of data in the electronic forms and the service condition, some of the machines were selected. Those machines are having centrifugal make, expander compressors, reciprocating and screw compressors. The subscription model is an OPEX model, and it is 5 years. It is under 5 years O&M. What is when you talk about the predictive maintenance, what are the key highlights which is applicable for a model is generally it is an AI ML based software solution, and idea is to develop a predictive analytics solution for critical equipments to handle the real-time data, to tell us if there are any alerts and notifications in the system, and to have a dashboard for visualizing the data trends and key parameters. Also, dashboard would be able to tell you about the warning signals for failures, and also if there are any residual life predictions. It can also tell you about the root cause analysis, and training of the model can also be carried out, and change management based upon the values which can also be fed to this. So basically a human bias is also one of the factors which is being added to this particular model to have a value out of it. This is one of the use case study from ADNOC. Everybody has heard of ADNOC. This is Abu Dhabi National Oil Company. So ADNOC has done in 2019, what they have done is they have given a Honeywell a contract in which they are assuming to give more than 2500 assets to make their way for being the digitally enabled oil player. For them, according to their key tagline is every oil drops counts, and to make that drop count they are making it digitally empowered, so that they can figure out like for how much oil drop, what one is the bad factor, which is the key factor, which is the lagging factor on which they can focus. And they are assuming that over $1.5 million is what they are assuming to have the saving after implementing their digital twin, and yearly savings of 20 to 25 million, which is their expected benefits out of this project that they have implemented. Now this is what the ABB has done it for one of their client NLs, and this is basically a hydroelectric power plant in which they have done a long-term contract in which they have covered 23 sites and 12 different types of assets have been covered, and 673 models have been covered, and asset libraries has also been created. As you can see, to show you about the glimpse of what kind of failure it can tell. So suppose if there is a fault of a combined bearing here, so that classifies into this combined bearing. And suppose there is a problem with the electrical problem, then that asset type belongs to the generator. So based upon the fault, an asset type has been created, and based on which the failure mode modeling is also being created. Now how they are doing is, they are assuming that with the help of achieving this, they are able to reduce the unplanned disruptions, and they can have better maintenance practices. And there is also a feature of fleet monitoring which will help us from the top how this model can behave in a particular fashion for across the different value chains of the company. Thank you.